Now we're going to take what we've learned about the normal model and look at a typical type of problem that is actually used in real life where the normal model would be appropriate. So let's say a cereal manufacturer has a machine which fills boxes of cereal labeled 16 ounces. The weights of the boxes filled by this machine fit a normal model with mean 16.3 ounces and a standard deviation of 0.2 ounces. In other words, if I took a sample of the cereal box, a random sample of cereal boxes filled by this machine, I would notice that the weights center around 16.3, have a standard deviation of 0.2, and approximately unimodal and symmetric distribution. So I can use a normal model to approximate it. The company's goal is to minimize the number of underfilled boxes while also keeping costs down for the company. So what the company does is it sets the mean fill weight a little bit higher than 16 ounces so that the majority of the boxes will be at least 16 ounces in weight. So it says, with this mean and standard deviation, what proportion of the boxes do we expect to weigh less than 16 ounces? So I have a normal model here with mean of 16.3, standard deviation of 0.2, and this is the weight of the cereal boxes in ounces. And so if I draw a normal model to represent this data here, here's my mean, 16.3. I'm wanting to know what proportion do we expect to weigh less than 16. Well, 16.3 is the mean, 0.2 is one standard deviation, so it's a little bit more than one standard deviation below the mean to get 16 here. And I'm looking for the area under the curve here. That's what I want to know. Actually, I'm going to move that arrow. Oh, so 16. So we're going to say x equals 16, and I want to know what's that area. That's what I'm trying to find out. Excuse me. So I can find the z-score for this by saying z is 16 minus 16.3 divided by 0.2. This turns out to be negative 0.3 over 0.2, which is negative 1.5. So this value is negative 1.5 standard deviations below the mean. So if I go and look at my normal table and look at negative 1.5, so here's negative 1.5 right here, I can see that 0.0668, or about 6.7% of the cereal boxes are below that value. So going back to my value. So the area, the probability that, and I'm going to write this in two ways, the probability that x is less than 16 is also equal to the probability that z is less than negative 1.5, which is approximately 0.0668. Now, could I do this on the calculator? Yes. Two different ways, using normal CDF. And this is where you might say, I like the calculator better in this case. So using the calculator, let's get a calculator page going. So we're going to go to Menu, 6, Distributions 5, Normal CDF 2. So I can go from negative infinity to negative 1.5 using my standard normal model like I just did on the table. Or, and this is where you might like this better, statistics, number 5, 2. I could say go from negative infinity to 16. So my right bound is actually 16, but that only works if I'm dealing with the original mean and standard deviation, which is 16.3 and 0.2. So if I use the original mean and standard deviation and the x value instead of the z value, same thing. So let's go back and write that on. I could use normal CDF using negative infinity. So this z-score is negative 1.5 here. So that is the number of standard deviations that 16 is below 16.3. Negative infinity, negative 1.5, 0, 1, 0.0668, or normal CDF using the original data values, 16, 16.3, and 0.2, also 0.0668. So 3 different ways to find that value. I don't care which one you use. However, I would like you for the present time to continue finding the z-score for any of the normal models that we find, because that is good practice right now to do that, because that is an important thing you're going to need to know for the AP test. Now, I need to answer the question. Because I'm dealing with a model, I want to give myself a little bit of a weasel word, kind of, hedge my bets a little. I'm not saying this is exactly how many cereal boxes, or exactly the percent of the cereal boxes that are below 16, but I'm saying I'm using the normal model to approximate it. So according to the normal model, I expect about 6.7% of the boxes to weigh less than 16 ounces. Now this might cause some problems for the company. That's a fairly large amount of boxes that are under the weight that they say that is on the box. So what would this company president want to do? Okay, so I've repeated the given information up here, which isn't necessary. I don't know if that's on your sheet or not. The company says the proportion you calculated is not an acceptable standard. They want to adjust the mean. They want you to adjust the mean so that no more than 4% of the boxes are underweight. What mean setting is needed? Okay, so in other words, I want to find the mean that goes with this standard deviation so that when I draw my model, if this is 16 ounces, that this is only 4%. So I want to know what the mean should be in order to make that happen. So x is equal to 16. Now in order to do that, we're going to have to think backwards. We're going to have to say, if the area is 0.04, what is the z-score? And with that z-score, with this x value and the standard deviation, what is the mean? So we want to know z equals what when the area equals 0.04. So we can find this on the table, or we can find this using the calculator. So just quickly on the table, we obviously know this is going to be when the z-score is negative, so I'm going to look on the table to find 0.04. Okay, see, I see 0.0401, which is really, really close. That is negative, let's see, negative 1.75. Okay, so we can, using the table, say negative 1.75. Remember, on our calculator, we can do the same thing using inverse normal. So we go to Statistics, Distributions, number 3. We put in the area that we want, which is 0.04. And we can find the correct z-score, negative 1.75. So we get the same thing either way. That one was pretty easy to find using either the table or the calculator. And eventually we'll do one or the other and not both, but right now we're doing both. So z equals negative 1.75 from the table, or I used inverse norm, 0.041 or 0, 1, and I got negative 1.75 with some other decimal places. So how does this help me? Well, I remember that z equals x minus mu over sigma. So now I know the z value that goes with this x value. This z value is negative 1.75 if I have this, if this is my area. And I know my standard deviation is 0.2, so I can say negative 1.75 equals 16 minus mu over 0.2. So 0.2 times negative 1.75 equals 16 minus mu. If I add mu to this side and subtract everything on the left side from the right side, I get 16 minus 0.2 times negative 1.75. I end up with mu equal to, I gotta find my notes here really quickly. I could do it on my calculator, but I already did it, 16.35 ounces. So the machine needs to be set with the mean equal to this. Now that means more of the boxes will be at an acceptable weight. All but 4% of the boxes will be at an acceptable weight, but it also means you're going to have a lot more boxes overfilled with extra cereal. So the president of the company says that new mean weight will be too expensive for the company. He wants to set the machine to a mean fill weight of 16.2 ounces, but also ensure that only 4% of the boxes are underweight. So what standard deviation would I need to have to make that happen? Okay, so in this case, I'm saying I want this to be 6.2. What does the standard deviation have to be? So once again, let's fill this in. We want this to be 16. We want this to be 4%. We want the mean to be 16.2. So I need to find standard deviation. Once again, I need to know what z-value this will be. Well, the z-value is only dependent on this percentage. We already know that if the area is equal to 0.04, then the z-score is equal to negative 1.75. We already know that's still true from the previous computation that we did. So all that's different now is when we do our z formula, we're saying negative 1.75 is equal to x minus mu, but now our unknown is sigma. So sigma is equal to 16 minus 16.2 divided by negative 1.75. This gives us a standard deviation of 1.114 ounces. So the machine would have to have a standard deviation of only 0.114 ounces. It says, what does this tell us about the machine? That would ensure more consistent fill weights or less variability in fill weights. That would be two ways of saying it. Obviously that would be the ideal. Now whether you could calibrate the machine to have such a small standard deviation would remain to be seen, but that's obviously what the company would like to do, is to set the mean lower so they don't waste extra cereal, but also have a more consistent fill weight so they don't have as many underweight boxes. What is the 85th percentile of the fill weights? Using the original parameters, so using that mean is 16.3 and standard deviation is 0.2, we want to know what x is if this is 85%. Now what we've done in the past is we said inverse norm of 0.85, 0, 1, and we got a z-score. And then we use the z-score to help us find x. So let's go ahead and do it that way. Now we could also look up 0.85 on the table and then go back and find our z-score that way, but I want to go ahead and just use inverse norm on this one. So inverse norm, I'm just going to grab and copy this, 0.85. So this gives us a z-score of 1.036. I'll just use that, 1.036. So z equals 1.036. So basically what I'm looking for is an x value that is 1.36 standard deviations above the mean. So remember that 1.036 being our z-value is x minus mu divided by sigma. So we could say here that the number of standard deviations, 1.036, times the standard deviation equals x minus 16.3, or 16.3, the mean, plus 1.3 standard deviations above the mean gives me x. So when I calculate that, X is 16.5073 ounces. Now here's where I want to show you something that I think you'll really like on the calculator. I can also do this more directly using inverse normal. I could also do inverse normal, putting in the percentage, but use my original mean and standard deviation, 16.3 and 0.2. So let's do this on the calculator. So I'm going to go back to my original menu, stats, distribution, inverse normal. So my area is still 0.85. I'm still looking for the 85th percentile, but I'm going to put in my original mean and standard deviation, and notice that gets me directly to the data value. I don't have to do the z-score first and then use the z-score formula to find x. I can go directly to x on the calculator. So this is where technology will save you some time. This gets me directly to 6.5073 ounces. So what would you need to show if you did the work this way? You would just need to show this work and do this on your calculator. Now what does this tell me? Hopefully you remember what percentile means. This means 85%. I'm going to say about, because remember we're using a model, so we're not exactly sure about this. It's an estimate. About 85% of the boxes weigh less than 16.5 ounces. Okay, so there's a good example of how you can use the normal model to help with quality control. And there's actually programs that do this in colleges where you're trained to do quality control using statistical methods like this.